Hey peeps, happy Easter. It's Good Friday and this is a Good Friday special because Uncle Kev is releasing part 2 of the 3 Degree of Freedom motion platform build early. So happy Easter guys. And I'm having a great time here this morning on Good Friday. The family's gone out to do other things and I'm in my workshop and I'm wearing my pajama pants. That's right, but they're the right kind of pajama pants. Oh yes. Ye old Ford racing, the only way to drive. Enjoy part 2 guys. Keep going with the build. You're going to get there and you are going to have a fat time once this is done. Happy Easter and we'll see you in part 3 in about a week's time. Yeah, well welcome back guys to part 2 of the 3 Degree of Freedom motion simulator platform base plate build. Now something I need to bring to your attention and something that I totally overlooked in the what tools we're going to need video was I forgot to include a hammer, a humble hammer, and a metal punch. Now you guys are going to need a punch. This is an old school style punch that you just belt the hell out of with said hammer, or you can buy the spring-loaded punches. They're not too expensive as well if you wanted to purchase one of those, but you will need to purchase yourself a metal punch. And you will most definitely need a hammer. But you will need these items because you're about to engage both of these to be able to continue with your build on our base plate. Now, ignoring this cluster, let's insert rude sexual reference, which was once a legal term, part here, we're focusing now on the back end of our base plate where our traction loss wheels run and where our traction loss motor sits. And the mechanisms that we need for that to all work as it needs to work. These things mainly being our plate that our wheels run on, okay? Some 25 by 50 millimeter by 3 millimeter thick box steel that we add for some bracing and for some rigidity on our plate because this plate will still flex a bit. This plate is 150 millimeters wide, right? It's 1,000 millimeters long, or if you like 1 meter long. And it's, again, 5 millimeters in thickness. Okay, you're going to purchase yourself some 50 millimeter in width by 25 high. Get it with a 3 millimeter thick wall. You will also get this box. This piece is a piece of scrap I had left over. It was only this length. You may as well get yours the exact same length as your base plate. So 1 meter of 50 millimeter by 25 millimeter, 3 millimeter thick wall, box steel. Here are our clamps that I was badgering on about. This is a wonderful opportunity to use them, and we'll talk about that in a second. You will need to set this up, keeping in mind that your box will be right at the end. So all this business that we're measuring here, you'll be doing at each end, not inboard like this one is. This box does not sit completely on the plate. See where our traction loss wheel's been running there? See how close it comes in the middle up here at its greatest arc? Right, there is also the caster wheels that are on the traction loss mid-frame. They also have to come through here and they have to clear this bracket, okay? That's why this has to be offset off the plate. Otherwise, this will interfere with the traction loss axle, rightio? That's why this box is set off the plate, but it's set on the plate enough to still do its job. You have to put a tape measure on your box and you need to measure in 30 millimeters. Measure in 30 millimeters along your box, okay, and make a mark. Make a mark on your box. You'll do it that side, then you'll do it this side. 30 millimeters in and make a mark. And then that mark is then lined up along the edge, the back edge of your base plate, both ends. So then your bracing piece of box here is straight. Okay, so obviously my piece is all made here. You're going to have these pieces as individual pieces that you can work with, which is good because they need to be turned over and welded on the other side. You're going to line those marks up as I've just described, 30 millimeters in along the edge of your box. It's a 50 millimeter width, right? So you're going to have 20 millimeters overhanging. There you go. You can look at it like that. You will have 20 millimeters outside hanging over the back of your plate. Make sure you've got that the same both sides. Then get your F clamps. Okay, we've talked about F clamps. I've been badgering on about them. Here's a great example of how to use them. Now, if you don't know how to use an F-clamp, you can do a YouTube search, learn how to do that. They're fully adjustable. If you can't work it out from there, it's time to go to the psychiatric hospital and seek some drugs. Rightio, I've just got a vice clamp here in the middle as well. You don't really need one in the middle. I've just got that for demonstration purposes. Vice clamps are also very handy. They're adjustable here as to how much force and how much clamping force they have. Again, you can trawl YouTube to work out how to use all these mysterious and wonderful tools. I was very unkind earlier and very lazy. Who gives people advice to go to a psychiatric hospital and seek drugs and medication if they don't know how to use something? An asshole says that sort of thing. And I'd like to think I'm not an asshole. I'm going to just show you very quickly the basic operation for an F-clamp, okay? This is our vice or our clamping part here. Right, this is our height adjustment for our whatever it is, whatever metal it is that we're clamping, however large our piece is, okay? This just does up, and what it does is it skews this part here on our shaft and clamps it. So all you're doing is moving this to the thickness of your piece, making sure that you've got a little bit of thread. You don't want this to be all the way through, like that, for example, and then putting it on your piece and then trying to do it up because you've already come all the way through. Okay? You've used all the thread already, so make sure that you have this at the, so your thread is all the way back, and then find the workpiece you're going to need to clamp. Here's the piece I prepared earlier, an example. It's a bit hard actually, this one, because it's so thin, but there we go, I can do it. And then you can do it up, and it won't work because that's too thin. So what have I got here? Here. Let's clamp our tape measure. Okay, so this is just an example of how to clamp shit. It's done up, and that's going nowhere. If I keep doing that up, I'll end up breaking my tape measure. I don't want to do that because it's not that old, that tape measure. Okay, that's how to use an F-clamp. Bring it together, you can tighten it up and that keeps it in place for moving it around the workshop. Where you've marked them, right, what you're going to do is you're going to just, like in our previous video where I showed you how to tack, how to do your tacks for your stabilizer foot, you're going to do the same, right? Just run a tack here on this end. Oh, except you're going to be out here, remember. Remember, yours is going to come all the way to the end, so you'll run a tack to tack each end of your 50 by 25 box so that it's in place and it's not going to go anywhere when you do the rest of your welding. Then you're going to run some small 30mm long beads, right? These are approximately 30mm in length. You're going to go zzz. Actually, you're going to go like this. Zzz. Then you're going to leave approximately a 90mm gap, and you're going to go because you've been watching all the welding videos on how to run beads, how to weave, how to do butt welds, and all that sort of stuff. And you're going to learn how to do that, and then you're going to come and go zzz. So guys, I'm just going to do a very quick demonstration of how to lay down a weld bead. Now, this is something I'm going to show you. It's something that you are going to need to practice, and it's going to take you some time to learn how to do this and not compromise your welds and not blow through your metals, especially if they're thinner metals. You're going to need to be patient, but you can fix them up, and you're going to get better at this with time and with practice, like everything, okay? Now, I've got a fan set up. This is my little battery operated fan. I point it towards where I'm going to be welding, so then it blows fumes away from where I'm breathing. In my workshop, I've got a large front door, it's always open, and my smaller door is also open to allow good ventilation. You can actually use a fan to quite successfully keep fumes and gases away from your lungs. So that's what I would encourage you to do. So let me set this tripod up now, and we will have a look at a little bit of welding technique. Okay, I'm just going to make sure before I start that that piece is doubly clean, because that's going to be important. So we'll get our wire brush, which is excellent for keeping this sort of stuff clean, and we'll give this a good run through here. Okay, I've got my clamp on, a nice clean part of our piece that we're welding. As I said before, it's important to have that clean. Now, we've talked about our wire. This is a little bit longer than 15 millimeters, but 15 millimeters is probably about what you want on your nozzle, okay? What we're doing is we're getting that weld in the gap here between our 50 by 25 box and our 5 millimeter plate. Now, our 5 millimeter plate is a heavier steel than our box. So for this particular weld that I'm doing here, I'm going to be concentrating on the heat being in the plate, and I'm pushing the pool of weld into my box, right? And what you are going to have to learn to do is you're going to have to learn to find that sweet spot of how fast you are moving and what your voltage, power settings and wire speed is. As I've mentioned previously, my wire speed and my voltage always sits at 12 o'clock. And then I adjust, depending on the gauge of the steel I'm welding, my speed. If it's a very thin metal that I'm welding, it'll be a very fast weave. I won't linger in one spot too long or I'll blow a hole in my metal, right? I can safely keep my welder going for a long time on 5 millimeter metal without ever blowing through it, okay? Especially a MIG. Even at its highest settings, it's going to take a long time to blow through 5 mil. Because we've got a 3 mil box here, we have to be a bit careful. Now, this is going to be something that requires practice, and you will learn over time how fast to move, because you'll start blowing holes in metal if you are not moving fast enough. But you don't want to move too fast, otherwise you're not going to get the penetration you need to do a good strong weld. That's the juggling act that you have to learn to become proficient at, okay? It's the combination of having enough penetration and heat, but not so much that you're ruining your metal. All right, with that in mind, let's do a little demonstration. This will give you an idea of how you need to do this. Okay, so I was really concentrating there on putting most of my heat and getting the weld pool to form on the thick metal, and I was pushing it into the box. Okay, now I'll clean this up with the wire brush. And a wire brush is absolutely the best way to clean weld, flux and slag. A wire brush like this, a round brush on a drill, does a fantastic job. This is going to take time for you to be able to get to that quality of weld. Don't stress about that, okay? You will get there, and you'd be surprised how quickly you'll get there. You can still see on some of these welds, and I need to point this out because it's important, see the pitting in some of these welds I've done. That's because it hasn't been cleaned enough, and we've got pollutants in our weld pool, right? It's on the odd piece of weld here. Some are good, some are not so good. Okay, so you can see here, I've done this earlier and I did this deliberately. This is what you are going to find happen to you. Let me just clean this up as well so you can see what's happened here, right? I'll have to repair this later. And you can see by the mound of weld there, okay, that the welder was left in the position for too long. It's blowing a hole in the box. That's what you're going to have to deal with sometimes, and you can see the weld's cold even in spots there, right? It hasn't actually welded into the bottom plate very well. This is what your welds are going to look like for a little while until you become more proficient in working out how fast you need to move versus how much penetration you're getting. Don't stress. That I will get a grinder on this, or what you would do is you would grind this back, grind those chunky parts of the weld off, and then you would patch that hole up with weld. And you will be doing that sometimes, guys, until you learn how to run your welds in a way where you're not burning holes in your metal. It's going to happen. Don't get frustrated. Just keep practicing. You can get scrap metal and practice on it for a long time. That's the way to do it, is to get flat pieces of steel and just practice doing long lines, right, of nice hot welds. As always, if you need help, we've got the comments there. We can work this stuff out via comments. We can get some dialogue happening in that regard. As I said, roughly 30 millimeters in length, approximately every 90 millimeters along until you've done the entire length of your piece of 25 by 50 millimeter by 3 millimeter thick box right along, okay? You are not going to do that without your clamps being in place, because if you did that, you should be all right if you tack these ends. It shouldn't go anywhere. But say, for example, that you forgot to do these tacks, you didn't bother with clamps, and you just sat your piece of 50 by 25 box on your base plate and you just started welding away happily. By the time you get to the other end, you're going to come back and go, oh, my metal's all lifting up. And you're going to look like an absolute arse clown. So that is why we use clamps and tacking in different areas to hold our metal in place when we really start putting in some serious heat, because metal warps, it moves, it'll just move. If it's not clamped, it will move. And obviously what's going to happen there is this will just lift up, and this will be lifted up, and it'll be very hard to push back down once you've got all those welds in place. So you have it clamped, so when you do those welds, it's staying straight. Then once that 50 by 25 is on that base plate, okay, then you can flip your traction loss plate with this now welded on this side. You can take your clamps off. Once it's cooled, take your clamps off, it's not going to move. Then you can flip it over, okay, and then on the underside, and hallelujah, I've got my stuff on a table now, because as you know, because I have mentioned this, I hate working on the floor. Then on the underside, you're going to do exactly the same thing. Right, 30 millimeter beads, approximately every 90 millimeters apart. Don't worry about this stuff here. This is all a part of that cock up I talked about. Right, so once you've welded your 50 by 25, top side, underside, that's done. It's now ready for us to measure up the metal we need to build our bracket that our push rod that goes to our traction loss motor is going to sit on. Let's talk about how we build that now. Before we get into building the bracket that our traction loss push rod runs to our motor on, I better actually explain what the hell we're doing with a 25 by 50 millimeter box, because you're thinking, yep, this guy has definite mental health issues. Well, we all know that, but the whole reason and the whole purpose for us adding this 3 millimeter thick box steel is to add rigidity to our plate. Okay, even though this is a chunky plate, right, at 150 mil wide and 5 mil thick, it will still flex. If we were to build this bracket and just weld it straight onto this base plate without adding any bracing to the plate, every time our traction loss with the weight of the mid frame, the top frame, and ourselves and all our peripherals, every time the traction loss motor was commanded by SMC3 and by SIN tools to push us one way or the other, and this was just welded straight on that plate would flex. It'd flex that way, right? When it was pulling us, it'd flex that way when it was pushing us. So what we do by adding this piece of 25 by 50 by 3 millimeter thick box right along in the way that I've shown you how, it makes the traction loss plate stiff. It stiffens it and it will stop it, and it does. It works like a dream. It is not black magic, my friends. It is not madness. It is science. I do feel the need to very quickly talk about the importance of the design in this 3-degree of freedom motion platform simulator, as far as how our motors attach to our frame and how we are isolating them using hardwood timber. Now, previously in the other earlier videos here, you would have seen a little piece of metal bracketing coming off this. I've now removed that because it's no longer in the build. Earlier in the build, I was originally running my traction loss motor connecting rod just off a metal bracket, a piece of metal that was welded on here, okay? But to show how important it is to have the grounds on our motors isolated from each other, because these motors are case ground, okay? So if they're all actually then attached directly to a metal frame, they all share the same frame, you're going to have issues with different currents running through your frame, which in turn will feed back into your IBT2 H-bridge controllers and your Arduino Uno, and they'll wreak havoc with those electronics. And they, in fact, and I know this for a fact because my rear traction loss motor would not work until I diagnosed the fact it wasn't working, because it was the only motor that I didn't completely have isolated from the frame because of the connecting rod from the shaft on the motor connecting in straight to metal, straight onto this metal frame. Therefore, its earth was travelling through the whole frame, and it was travelling back to the IBT2s, and it was just shutting the motor off in the SMC3 utilities. Dunk, and it would turn off and it wouldn't move. And I was like, what the hell is going on? And then I realised, well, look, this is the only motor out of all of the motors that has one part that's going to metal that really can actually earth or energise back to the frame. So I inevitably ended up redesigning the bracket here and running the actual connecting rod from the shaft into timber, so then it actually had some isolation from the rest of the frame, and voila, like magic, suddenly the motor was working again. So it proves the point that you really do have to have those motors and their grounds isolated from each other. If you get a dry timber, in our case it's hardwood because we need it to be strong because of the forces it has to cope with, that will isolate current, okay? We're not talking about 20,000 volt overhead power lines here, we're talking about 12 volt DC, and hardwood timber, dry hardwood timber, is more than adequate to do that, and the proof's in the pudding because that's what I'm using and it works. Right, so what you're going to do is you are going to cut two 250 millimeter in length pieces of your 50 millimeter by 8 millimeter thick steel that was in the materials list to buy. You're going to cut one 250 millimeter length and a second 250 millimeter length. You are also going to cut a length at 200 millimeters, which will become your gusset, your bracing. Okay, so before we put our bracket together, you're going to have your two individual pieces of 250 millimeter 50 by 8 millimeter thick steel. You're going to get your tape measure. You're going to measure across 30 millimeters. Okay, make a mark. Make a mark sort of at the top end of your 250 millimeter length. Do the same the other end. I've used a square here, so if you've got a long enough square, you can use that. But if you don't, then you can just measure 30 millimeters inboard at both ends, okay? Then between those two 30 millimeter marks, you can put a ruler and then you draw a line straight down. Now this is not in the center. It's not in the center, it's offset. And we'll go into why that's offset very shortly when we talk about our Merbau that goes on. It will become apparent why it's offset. 30 millimeters, make a mark. 30 millimeters, make a mark. Then draw a line straight down between the two marks. Then you will measure from the very top. You will measure down 25 millimeters. Okay, make a mark. Put your square on, right, and then draw a line across. Then you will measure 55 millimeters from this mark down, make another mark at 55 millimeters, put your square on, and then draw your line across. And what you will end up with, now it's hard to see because I've already drilled where those lines intersected, but you will end up with this scenario. Okay, then what you're going to do is you're going to take your punch, your metal punch, you're going to place it right in where those lines dissect. You're going to get your hammer and you're going to hit the bejesus out of that. One hit. Don't hit your fingers, otherwise it'll be another trip to the hospital. Okay, so we're going to do that on our 250 millimeter piece before we build our bracket, otherwise it's going to be even harder to do all of this. Okay, so we prep this and drill this first, and then we can weld it together. Okay, here we have our three pieces of our 50 by 8 millimeter thick flat steel that we've cut at 250 millimeters in length, 2 of them, one of them at 200 millimeters. So I thought I'd be a nice guy and start right from scratch with that bracket, so then we can learn how to build it completely, including getting our punches, getting our marks punched here. And I'm going to show you how to do that. I know I went a bit crazy before saying that you needed to hit the bejesus out of it, and you don't need to. Okay, you don't need to. You just need to get your punch right in those intersecting lines. Right, one good hit like that. As I said before, try not to hit ye old hands. This is what you would expect your punch marks to look like after you have punched at these intersecting lines. Rightio, so it gives enough indentation in the metal so then when you start with your drill bit doesn't just wander all over the piece of metal, because that is what will happen if you don't pre-punch where you're about to drill. Okay, so there's only a couple of occasions where you are going to be required to do some drilling in this build. Our rear traction loss bracket is one of these occasions. So I'm going to show you a couple of tips that should make your experience with drilling go a little bit smoother. Now the trick with drilling metal is that you do not drill at high speed. Okay, you need to go the lowest speed that you can possibly go. Now with this drill I'm about to use, a little battery drill, my speed is controlled with the trigger. So the lighter I press it, the slower it goes. As I press harder, it speeds up, okay? Now, with a system like this, basically you need to drill, you need to find the speed, that's the slowest speed you can drill at without the drill bit actually stalling, okay? You don't want to drill too fast. All you'll do is create excessive heat between your drill bit and your metal, and you'll end up blunting your drill bit, and then that's it. You'll no longer be able to drill. You'll either have to get a drill sharpener or you'll have to go and buy another drill bit. I highly recommend using some type of cutting fluid. Now WD-40, it's not a cutting fluid, but it will suffice for the amount of drilling you're doing. Okay, it basically will act as a lubricant. It will also help keep things cool. So keep your drill bit sharper and make your drilling a little bit quicker, a little bit easier. That's one tip. The other tip is to do a staggered drill. Okay, so these particular holes for our traction loss motor bracket are, as mentioned before, they need to ultimately be 8 millimeters. All right, we could attack it with 8 millimeters straight away, but it's going to be harder to drill because your drill has a larger surface that it has to try and drill through from the get-go. So frequently what people that drill a lot of metal will do is they'll do a pilot hole. So you'll use a smaller drill to actually drill through your metal first. It makes your larger drill bit's job a lot easier. So that's what we're going to do, okay? So what you'll do, now you'll notice that I have this on the floor, because now you'll find it really easy to have a downward pressure because you can stand over your workpiece, and therefore you'll be able to actually look down at your drill as you're drilling, and you'll be able to see a lot easier if you're crooked. If you're drilling on at angles, which you don't want, you want it as straight as you can get it, because you want a straight hole to be your end result for these two holes. So we're starting with a smaller drill bit. This is our 8mm drill bit we're going to finish with. This is a 5mm drill bit that we're starting with. Rightio. So we'll whack a little bit of WD-40 where we're about to drill. Okay, you'll stand over your workpiece. You'll put one foot on your workpiece. We've got it on a wooden block, so then when we go through, we're not bashing into the concrete and ruining our drill. Okay, so I'll be having pressure pushing down on this drill, and we're going to try and drill as slow as we can. Now, we'll get rid of the chips, give it a bit of a break. We'll go with a little bit more WD-40, and then off we go again. Nice and straight with good pressure. Righto, we're nearly through there. We're nearly through, so therefore the drill has suddenly locked. Okay, so I'm putting the drill in reverse and I'm coming backwards. Now I'm going forwards again with lighter pressure. There we go. We're through. Right? So you don't need a drill press. I've got one, which is handy, but you don't need it. If you just concentrate and get a little bit of technique going. Nice and straight drill again. Okay, give it a break. A little bit of WD-40. Go again. Through. Okay. Now I'm cheating a little bit here because this bit of scrap I had lying around is only it's only 5mm thick. You're drilling 8mm, remember? So yours is going to take a little bit longer. But with the smaller drill bits, it's surprising how fast a good sharp smaller drill bit will get through metal, even thicker metal. Okay, so we're putting our 8mm drill bit in now. This will be our finishing. This will be our finishing hole size. A little bit of WD-40 again. Foot on the piece so it doesn't move. Downward pressure, not too fast. Righto, stop. A little bit more WD-40. Clears the chips for us. And we're through. Okay? Same again. Nice straight drill. Bit of pressure. Not too fast. Right, we're almost through there. You're not going to be that much longer getting through your 8mm. You've only got another 3mm. Righto. We're through. Okay, a little bit of patience, a little bit of technique, and you won't have issues. Please follow what I've said, otherwise you're going to be pulling your hair out with blunt drill bits. You need a little bit of some type of fluid you can use as a cutting fluid. WD-40, it's a anti-rust, it's just a fish oil, kerosene mix, I think. But anything that will give you a little bit of a cutting fluid type of arrangement to add a little bit of lubrication to assist your metal cutting, because a drill bit is cutting metal. Okay, slower speed on the drill, little bit of lubrication. Have your workpiece so then you can really keep it clamped, like what I've done. The good thing about doing it like this is you can push down, so you've got lots of strength to push down to get through your metal. Good luck, guys. If you need help, you know you only need to hit me up in the comments. This is a side note, guys. I can tell you I just had one hell of a splinter, metal splinter in my fingers. This is something you're going to encounter frequently while working with metals and cutting metals, okay? Because you can't always wear gloves because they're cumbersome. And you are inevitably going to cop metal splinters in your fingers, in your hands. You just don't want to get them in your eye, okay? I've mentioned before that I have had one clanger of a metal splinter in my eye that I didn't do anything about because I thought it was just going to go away, and it didn't. And after a few days I ended up having to go to the hospital, and it had to be removed from my eyeball, and by that time it had started to rust in my eyeball. This is what happens, and you end up with what's called a rust ring in your eyeball. And then guess what they have to do? They have to get a little mini grinder. That's right, they fill your eye with dye. And for 3 sessions, I had to go into the specialist, have dye put in my eye via a needle, and then they get a little grinder and they grind your eyeball with your eye open to get that rust ring off, because otherwise it will blind you. So this is why I cannot overstate to wear something to look after your eyes particularly when you're angle grinding. And I had safety glasses on when I copped that splinter in my eye. It came in the side of my glasses into my eyeball. That's why the full face shield is the way to go. Please get one of those so then you don't go into that. Get yourself a couple of pairs of tweezers to have in your workshop, and maybe a set of magnifying glasses that can go on your head so you can find these splinters, because they're really small and they can be hard to see, but believe me, you'll know they're there. So get yourself some tweezers and a magnifying headset, so then when you do get splinters, you can get them out. Don't leave them in your body, get them out. So what you're going to find on the back side of your piece of plate now that we've just drilled is you'll see all the nasty business on the back, right? So we just need to clean that up. So where your drill bits come through and pushed the metal out, those bits are quite jagged and sharp. We want to clean them up. Right, we get our trusty angle grinder once again. And we give our surface a nice smooth over, okay? So no jagged bits, no nasty bits to send us to the hospital again. We're going to have to leave it at that, guys. Quite a long video, this one, but there's a lot of content that we needed to cover in part 2. I can't see part 3 being any different. I'm a little bit surprised, actually. I thought I'd get through a lot more than I have. But anyway, we're including a lot of detail in this, and that's what we want. We want detail, so then you guys know what you're doing. So I have to assume that you guys don't have quite as much knowledge with all of this sort of stuff that I do. Some of you might, and you'll just breeze through this. Others may need a little bit more direction, and that's fine. I'm happy to do that, okay? That's how we learn new stuff. That's how I learned stuff to start with, because I didn't have a clue what I was doing when I started with this sort of stuff many years ago. And I'm still learning too. Can I just throw that one in there as well? That way it sort of gets you off the hook if you do something wrong. We're all always learning. Thank you very much for everybody who is subscribing. Thanks, guys. And for those that have freshly joined us, please subscribe. I'm helping people out here who are wanting to have a crack at building a 3-degree of freedom motion platform. And I appreciate it if you help me out by subscribing. Helps me out eventually, you know, if I can get enough subscribers and enough support, it's going to help me to maybe purchase different things. I'm planning on doing more projects after this. I'm thinking about building an electric scooter after this. I built an electric bike not that long ago. I'm thinking about having a go at one of these scooters. I don't know, maybe people can let me know if they'd be interested in us doing something like that, for example. Don't know. Maybe you think, mate, that's going to suck balls. Why would you do that? Or maybe you think that's a great idea. But anyway, I'm just throwing it out there, okay? I'm thinking about what other future projects may be that others may be interested in. So, guys, we'll see you in the next video, eh? Hopefully in about a week. I'm trying to keep these at week intervals, and hopefully in another week we'll have part 3 of the base plate for our 3-degree of freedom motion platform. Catch us then.